Hi, welcome back to our calculus video series. Today we're talking about the average value of a function, which is just the average of the integral value from a to b. It's the average of all of its values from a to b. So for example, if I wanted to find the average value of the function f of x equals 1 plus x squared on the interval from -1 to 2, I'm going to have to take 1 over 2 minus -1 times the integral from -1 to 2 of f of x. If I do that, I'm going to get a value of 2. Because what that really says is 1 over 3 of this function, which is 1/3 times 6, which is 2. So if you integrate it, you get a 6. But then if I divide by the 3 or multiply by 1/3, I get 2. So my average value of f of x on the interval -1 to 2 is 2. And the mean value theorem for integrals says that as long as this is continuous on that interval, which it is, there should be some x value such that if I find x, f of x is going to equal, in our case, 2. The average was 2. So what I'm going to do is I'm going to say 2 equals 1 plus x squared. So there should be at least one value such that f of x equals 2. So I got my integral, I solve it, it's 2 for the average. So I set 2 equals 1 plus x squared. I subtract 2. And I factor, and x is positive or -1. Now we can check this graphically. From -1, let me make this purple. From -1 to 2, the average value of this function is 2. And it looks like I've got two intersection points at x equals -1 and x equals +1. Where f of x is 2, or y equals 2. So there should be at least one. In our case, we got 2. Alright. So, for example 3, I want to show that the average velocity of a car over time, t1 to t2, is the same as the average of its velocities during the trip. The average velocity is the position at time 1 plus the position at time 2 over 2. The average of its velocities is the integral. So let's say car goes from mile marker 100 to mile marker 150 in, or maybe we'll say 300 in 5 hours. That would be 200 miles in 5 hours. That would be 40 miles per hour on average. But if I wanted to find the average of its velocities, I would need to take the integral from mile marker 100 to mile marker 300 of its function that describes the velocities. A couple notes here. just to remind us of what all this calculus stuff does. the integral of velocity is position, or the derivative of position is velocity. So if I take the integral of, we could say velocity. If I take the integral of velocity, it's going to give me position. If I take the derivative of position, I get velocity. All right, so with all that in mind, let's work on this one. We could say that let me do this in blue. We'll say that the distance traveled by the car is, we'll say delta x. And the time is delta t. So difference in x, difference in time. So average velocity is going to be delta x over delta t, distance over time. We could also claim that delta t can be written as t2 minus t1. So this is the same as delta x over t2 minus t1. So that's if I wanted the average velocity. If I want the average of the velocities, layout margins narrow. If I want the average of the velocities, I'll do this in purple. The average, that's hard to read. I'll do it in green. The average of the velocities is going to be the integral from t1 to t2 of our velocity function with respect to t. We know that that's the same as integral from t1 to t2 of, we could call this f of x for position prime, or f of t, maybe I should say prime dt. So velocity is just the derivative of position. Well, if I were to integrate this, what I'm going to get is, I'm going to get one over t2 minus t1 of, and then this is just going to be f of t2 minus f of t1. And what is this? That stuff right there, that is the difference in the position of the car, which is delta x. So let me insert a shape. Nope, shape. There we go. This stuff right here, f of t2 minus f of t1, is just the difference in position. So this is the same thing as saying delta x over t2 minus t1. Same thing. All right, so let's look at one more example. Example 1. One more example from our textbook, if I can find it. Where'd it go? There it is. Let's say I wanted to find, let's do this one. Number 18. A cup of coffee has a temperature of 95 degrees Celsius and takes 30 minutes to cool to 61 degrees in a room where the temperature is 20 degrees Celsius. I can use Newton's law of cooling to show that the temperature after t minutes is this function where k is 0.02. So what that is saying is take 61 degrees equals 20 plus 75 e to the negative 0.02 t and if t is 30 minutes, I get something pretty close to 61. It's not exactly perfect, but it's pretty close. For part B, I'm asked to find what is the average temperature of the coffee during the first half hour. So that means I want to find what is the integral from 0 minutes to 30 minutes for the first half hour of 20 plus 75 e to the negative 0.02 t dt. And if I do that, let's see, math, 9 fn int 20 plus 75 e to the negative 0.02 x 0 30. And then I need to take that and I need to multiply that by 1 over 30. So I'll divide that by 30. And my average is going to be 76.4 degrees Fahrenheit. Now if we took this a little bit further, I could say, okay, what about the next half hour? Well, if I wanted the next half hour, what I would need to do is 30 to 60, and I could find that, whatever that is. So that would be, if I do 30 to 60, that would be like 51 degrees approximately. Or one more, 19. The linear density in a rod 8 meters long is this function, where x is measured in meters from one end of the rod. Find the average density of the rod. 12 over root x plus 1. So it would be 1/8, and then the integral from 0 to 8 of 12 over the square root of x plus 1. dx. So math 9, 12 over square root of x plus 1, x 0 to 8, and then don't forget to divide by 8 or multiply by 1/8. The average density would be 6, and what's our units? Kilograms per meter. Kilograms per meter.